Okay, so orbital diagrams, these are all the same elements before, but if you're feeling uncertain about your electron configurations, then you should definitely, sorry, checking to make sure it's still recording through my headphones, you should definitely be practicing these again. Just write them out again. You come back and compare them. But we're going to do our orbital diagrams, and we're going to use shortcuts for all of these. So we're not going to take all the time to write out these super long configurations. Or super long orbital diagrams. Now, our orbital diagrams pretty much reflect our, I guess I can go up to this periodic table because it's got the markings. They pretty much reflect our electron configurations. So electron configuration is like the 1s2, or sorry, yeah, well, it'd be 1s2 for helium, or the 2s2 for beryllium, or the, 2p1 for boron. But now we're showing exactly how the electrons are arranged in those around the atom. So are they paired up? Are they in separate orbitals? So for beryllium, we can start out with the shortcut of helium. And then this is going to be 2s. And you can use either an underscore sort of line or a box. I like the line. Beryllium's electron configuration, actually if we scroll up here, is 2s2, helium 2s2. That 2s2 there means 2 electrons. So when we're filling in electrons here, our electrons are drawn as half arrows up and down. We have to have one up and one down. The order doesn't matter. It could be down and then up, or up and then down. So that would be the orbital diagram for beryllium. For boron, same shortcut, helium. And then this is also going to be a 2s2. And then it's going to be, we have to write out all 3 of these orbitals. It's going to be 2p. Now, how many are in the 2p? Let's go up and let's look at our electron configuration. There's 2s2, 2p1. So there's only 1 electron in the p orbital. Coming back down, that's 1, 2, and then 1 electron in the p orbital. For aluminum, we're moving down a row. So boron was here, aluminum was here, or aluminum is here, I should say. It's down below. So our shortcut's going to be neon. And I'm just kind of showing you different ways to do this. Then it's going to be 3s2, 3p1 as the electron configuration. So neon now instead of helium, 3s and 1, 2, 3, 3p here instead of 2s and 2p because aluminum's in the 3rd row. So there's 2 electrons here, 1, 2, and then 1 electron in the 3p. And you can see that looks very similar to boron. All right, so for sulfur, we can go up, we could either stop at the periodic table or we can just see what our electron configuration is from the previous problems. So neon, 3s2, 3p4. Maybe I should copy these over. All right, so this is the information that I'm working on. Put a little bit in my head. So we're going to do neon, and then I've got 3s, and I've got 3p. The electron configuration tells me how many electrons using the superscript. So the superscript says there's 2 s electrons in the 3s. And now this is the first time we've had more than 1 electron per orbital. So we're going to have 3p4. That means that there's 4 electrons, but I've got 3 separate orbitals. So they have to fill in one at a time first. Remember, we use the analogy that these electrons are like people in a really discount hotel. And so if there's only 3 people, they're going to get their own bed first before they have to share, right? As long as they're strangers, of course. And then my 4th electron is going to have to pair up with one of them. And it has to pair up, just like I had in the 3s, it has to pair up with opposite spin. So I tend to always just put it in the first one, but it doesn't have to go in the first one. So we used this over here, but we don't, didn't need to write that. That's not part of the problem. Right, so that would be for sulfur. For calcium, well, let's just go up and get our electron configuration from here. So that's calcium, copy, and paste it over here, and we can erase that. So I've got argon, that stays the same. And now I only have the 4s. So this says 4s2, so 2 electrons in there, 1, 2. Right, so some of these are simpler. And again, we can kind of look at like, oh, beryllium was helium, and then 2s2. Calcium is argon, and then 4s with 2 electrons. And if we go to our periodic table, they're in the same row or same column, right? So they're going to have the same electron configuration. All right, so gallium. Let's go see gallium. So unless you've really got a handle on your electron configurations, you're almost always going to want to write out the electron configuration first before you go do your orbital diagram. So this is interesting. So we don't just do valence electrons. We've only had valence electrons so far, but here our d electrons are not valence electrons. Shortcut's the same. 4s. And then we have 3d. 3d has 1, 2, 3, 4, 5 orbitals. And then we'll have 1, 2, 3. That's my 4p. And again, our electrons 2, 10, and then 1. So this will be 1, 2, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Even though I know it's going to be full because this is already saying 10 and I've got 1 electron in my p orbital, it's always maybe best practice to just fill them in one at a time first and then go through and pair them up. And then I'm going to add my last electron into that 4p. All right, now iodine. Come up here. If you missed all of these, watch the previous video. Worked through them all, albeit somewhat quickly. Get rid of these extra boxes, extra circles. Okay, so for iodine, krypton, and then we have a 5s, and a 1, 2, 3, 4, 5, that's 4p, and 1, 2, 3, that's 5p. And again, we just fill in our electrons, 1, 2, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now my p orbital, I need to fill in 5 electrons, 1, 2, 3. And so those ones are all those are single electrons. I need to pair up the last 2. So 1, 2 get paired. All right, so now barium, the last one here. Be nice and easy. Copy this. Because when we're using shortcuts, right, shortcuts exist for a reason. I start with xenon, and then the only orbital I have here is the 6s, and that gets 1, 2 electrons. Just like that. Now you might be thinking, how do I remember how many orbitals there are? Oh, I made a mistake here. That should be a D, or D, excuse me. How many orbitals do I know that there are? Well, every d orbital is going to have 10. Every p orbital is going to, every d orbital is going to have 5. Every p orbital is going to have 3. Right? 4d, that's 5. 5p has 3. And you can get that on the periodic table. It does require that you remember a little something else, right? For every orbital, we can hold 2 electrons. So since this basically represents 10 electrons filled into the d orbital, that 10 divided by 2 gives you the fact that there's 5 orbitals in the d subshell. And for p, there's 1, 2, 3, 4, 5, 6. So divide that by 2, that's your 3 orbitals in the p subshell. So s equals 1 orbital, p is 3 orbitals, D is not 10, 5 orbitals. So it doesn't matter which row is in for orbital configurations, they'll always have that many. All right, I'll catch you in the next one.